Welcome back. Now today we will make a video. What is that? So today again let's come back to our original topic, which is the main motto of the channel. We will talk about quantum mechanics. Okay, so today let's talk about how do we start this? Because today the topic is random. In quantum mechanics, we will talk about every possible thing we can in this video. So let's talk about, yeah. First of all, let's start with Schrödinger equation. Schrödinger equation. I have made a video on Schrödinger equation, how to derive it. So I will not go into a derivation. I'll just write the equation. We'll talk about the properties of this equation. H bar I h bar d over dt of psi of x and t. Why did I put this on? And the color is very weird. Psi of x and t, and then before that we will have this. This is a time derivation, okay? Equal minus h bar minus h bar over 2m d partial d x square partial d, not partial d, partial square, and d dx square, and this will be psi of x and t plus vx and t, and here there is also psi of x and t. Okay, I have made video on psi of x, but I never told why we are applying psi of x to every single operator, because everything in every the color is I think way too weird. No, that's better. Every quantity in quantum mechanics is taken as operators. Okay, everything is operators. Then okay, then when we talk about the operators in quantum mechanics, there is a rule that every operator will be multiplied, or will have a psi function or a wave function. It should be applied to each operator. As we see here, it's applied to this one over here, then over here. This is actually, if I write, it's actually an energy operator. Energy operator. Okay, this operators have some special symbols like this, and this is momentum operator, this is gradient operator, this is potential energy, or potential, sorry, that was a very bad word, is a constant. Potential energy is a constant. Wait, I think this is not clear, so let me write it on page. I of h bar d over dt psi of x and t. This is a energy operator. Energy operator, and minus h bar. Actually, here one more thing, minus h bar, huh, minus h bar d, wait, what is it, minus h bar over 2m d square psi of x and t over d of x square. Actually, do it this up, sorry, this minus h bar square is not the same, it is a square, is not the same, it's actually, the real one is of momentum operator is I h bar d of dx. Okay, here the problem, here the this I was removed because the equation was H Hamiltonian mechanics, which is also known as energy operator. It was equal, this equals p square over 2m plus v of x and t. Okay, here because of this square, because of this square here, that I vanished, because we know that I is equal to square root of minus 1, and square of I will remove this I, this square minus 1, and I equal minus 1, and minus 1, and since we have a minus here in this equation, what will have, that minus something which is inside of minus and an outside minus will give us I as positive 1. So that's why it's not added. So then that's why it's a, okay, this is a momentum operator, and then here again this d over dx is a gradient operator. The full form is square z, because of the square we take the second gradient operator. This is a gradient operator, gradient, it takes care of the gradient of the wave function, gradient operator. Then psi of x is the main, it's a wave function which applies to every single equation. It shows, if this is a let the basic example of psi of x is, if, okay wait, if this is a platform, on this platform we have particles and we don't know where they are, we don't know where they are, just made them using function or psi of, using a wave function, and we take double, let's suppose this psi of x, psi of with the property of looking at the particles x and time, sorry, position and time property, we can know of this wave function that where the electron would be found, the probability of finding electron higher in that area is when we take the square of this psi of x, psi of x and t square is this function, and this is a this function, this. So here, over here, chances are high, but here it's low, high prob of particle here, low prob of particle here. Okay, so then we have, I think we talked about Schrödinger equation. This is the main equation of quantum mechanics. Then let's talk about what do you call those, uh, gradient, no, it was ladder, yeah, ladder operators, ladder operators. let's talk about ladder operators. Before that, let's talk about it will cause, or it will have to be related to energy levels. Energy level related. So when it jumps up in level, what happens that there are two types of ladder operators: creation and annihilation operator. Here, when electron gained energy from the photon, okay, when it gained the electron energy from photon, it went up in level, it went up in energy level, and then we call this a creation operator. The the electron raised in level, but for when it goes down, after we know that 10 minus 8 seconds, this is the maximum time a particle can be in excited state, and over here when it comes down, it will it will emit E equal hf. It will emit energy, and this energy will be related to uh, the electron. Mostly we take electron. The electron decreased in level. Okay, so if it rises, it's a creation operator. If it goes down, it's a annihilation operator. And this is related to harmonic oscillator later. And what is that one? Quantum harmonic oscillator. And we know that the energy levels are taken as wave function. I just made random, so it doesn't matter. So here the wave function, and electrons are here. We know that electrons should be here, here, and here. Not should be. High prob, as we know that this will just give us the probability of electron being here, but it will not be here. Okay, so they are here. One more thing, energy levels are discrete. E1, E3, E2, E1. E1 being the lowest stage, lowest level, sorry yaar, level, and then these two are uh, in lowest and excited level. Only the, and this one is also known as ground level. Okay, one more thing about, there was a topic of light, and yesterday light, when I was making a video on light, I discussed the properties of light, that when electrons gain energy and go up in level, then decrease energy and go down in level, in this process energy is released. So the purpose of the mirrors in the gain medium, it was, this whole medium is known as gain medium. Okay, here the purpose of the ladders is the mirrors. These are mirrors, mirror 1 and mirror 2. The purpose of the mirrors is actually to in to keep process in that area, to keep the process continued. I don't know how to spell continued. I'm a shameful guy. Okay, so then this is the best example of this, taking the hydrogen atom or hydrogen element. It has one electron. The electron rises up in level, it will give out energy, and if it will decrease, no, it will rise means it will take in energy, and when it come down in level, it will give out energy. Give and take. Okay. Then what else? What else we could talk about? We could go on to uh, let's talk about how can we do this in terms of okay, we talk about this. The one more thing in quantum mechanics, the most common atom QM fact, hydrogen, or I think most of the other fields as well, they take hydrogen as uh, the important one, or they take do experiments on hydrogen one, as it only has one electron. It's in its outermost shell, so it's easier for them to study the hydrogen. And then there's something known as hydrogen spectra, and the hydrogen spectra can also be studied. And there's something known as hydrogen spectra, and that hydrogen spectra, if I draw it in terms of energy level, you might have noticed something here. Not only hydrogen, it can be many other, but I'll take hydrogen as as the main common one. The thing is, the levels the levels are limited and at a distance, because you will not get any other value other than the values of these, as will not get any other value in between the levels, or even above them, above them. And electron can either be in this, and this, and again this is the lowest point, lowest. And we can calculate the E equal HF, or not E equal HF, we could use here one more thing, electron is measured in this quantity. It's the same thing, but it is actually, if I want, it's E equal electron. This is nothing but electron volt. The unit is electron volt. This is actually electron volt. This is how mostly most spectras present energy. But not an issue, because if I want to convert this into energy, I'll just do that energy, or that energy level times 1 over 1.6 times 10 to the power minus, what was that value, minus 16 ish, equal the energy level over here, EV, and you multiply it with this with the EV, we get the energy level. So this is how we can convert EV into joules. And I mostly prefer energy level, because energy it's most simple, and then we can use the Broglie equation, the Broglie, wait, what is this equation? The equation of wave, the most famous, which is E equal hf. Then we can simplify this into E equal, this I'm just giving example, E c over s, and then we also have P is equal to h over lambda, and h is here Planck's constant. We know that E equal mc square, right? And P is equal to h over lambda, and we also know that, because there's an equation, if I'm right, this and this, E, what was that equation? I think, yeah, this one, hc over lambda is equal to P and h over lambda, and we can replace lambda with uh, lambda with h over P. Put this here, we get E equal h times h, oh no, wait, uh, 1 over h, and this will be 1 over psi is equal to P over h. Am I right about this? I'm just making it up. I'm not sure if it's right or wrong. C square. H just cancel each other, and then we get E is equal to PC, and here P is equal to E over C. Ah, I just made the equation for energy and energy momentum. So then physics, then what else could be, okay, this equation, and this is one of the famous equations, these, and of course then this, and also yeah, how can I forget the main Heisenberg uncertainty principle? Heisenberg uncertainty principle, the main thing in quantum mechanics which makes it such a phenomena, that E or momentum and x is equals to This main equation is the best of them all because this shows uncertainty, oh sorry, t, can't can't know each. I'll not do the mistake as common people do. Can't know each quantity accurately. Here is the difference. Accurately. Can't know each quantity accurately because most when we talk about depth of quantum mechanics or Heisenberg uncertainty principle, we have to be careful this with this saying here because most people may think of it as wrong pronunciation. It's actually can't know each quantity accurately. It means you know the distance or the position. It's high. The measurement on p or momentum will decrease. So I can say E this dot this P equal a constant, a constant. They're inversely proportional to each other. Inverse, inversely proportional, proportional. What the hell? I can spell proportional. Proportional. Okay, here. Then they are known as in a momentum position of momentum position Heisenberg uncertainty principle. If you know its position, it's a particle. If you know its momentum, it is a wave. Vice versa. And yeah, till here we'll talk about this much. That's it.